So we now have a somewhat complicated expression. The differential for the cash position is always the same. We have a riskless position. We don't expect there to be a DZ term. The differential of our cash position is simply going to be R times W dt. So now if we apply Ito's formula, Ito's lemma, then we have, first of all, the expression here for Ito's lemma applied to the long bond. And then we have N, the application of Ito's lemma to the shorter bond. And then we have our cash position differential. So if we look inside the brackets of the long and the short position, we see we have some dr terms, that's where the risk is, and we have some dt terms, which are, of course, not risky. So if we're interested in eliminating the risk in di, we need to eliminate the dr terms, which contain the dz terms, the Brownian motion. In order to do that, we just simply observe what's the coefficient of dr and set it to 0, and we get that n, it has to be a ratio of basically a multiple of the term and the price of the 0. So for example, if we were dealing with a 30-year 0 and a 20-year 0, in the numerator would be 30 times the price of the 30-year, in the denominator would be 20 times the price of the 20, or did I say 10 times the price of the 10? But anyway, you see the point that imagine time t is today, and we're looking at zeros of different maturities. So it's just simply that ratio. For this value of n, we can now go back and determine what the formula is for I, and here's the formula for I. And this now, of course, tells us what the value of W is. So we can choose W to make I 0 initially, or we do not have to. We can make W a free variable, or we can make I equal to 0. We then, by inserting n, this value of n, into our prior formula, we end up with this equation. And this equation is very important because what it tells you is that the differential of I is equal to the risk-free rate times the initial I value. So if the initial I value were 0, this is just a little bit of algebra that I will leave to you. If the initial value of I were 0, because we chose W to be that, this first term goes away. But the point is, whether it goes away or not, we see an arbitrage in this equation because we're told that the differential in I is the risk-free return on I plus something. And I can easily make this second term positive. First of all, we see this expression as risk-free. There's no dz term. So I have the phenomenon that di is the risk-free return on I plus something, and I make this second term positive by making T2 bigger than T1. So it says if I go long, the longer 0, short, the shorter 0, indeed, I will have a portfolio that earns more than the risk-free rate. And if I chose W so I was 0, I would have a portfolio with an initial value of 0 that makes a certain profit. Either way, an arbitrage. So the conclusions are that this n that we calculated eliminated dz, it eliminated the Brownian motion, eliminated all risk. And for no matter what value of W we chose, it was always the case that di was greater than the risk-free rate, or di was positive if we made I 0, unless there's no volatility. And of course, if there's no volatility in the market, if we go back and look at the process for R and eliminate the volatility term, then we eliminate the possibility of arbitrage. Because what we're saying is that there will just simply be drift in the portfolio. So the yield model, although it wasn't terribly realistic, it wouldn't have been obvious without a little bit of work, and this is the kind of work that needs to be done in these models. It wouldn't have been obvious without that work that this was a model that was actually fundamentally flawed, and it allowed arbitrage in our market. And of course, if we have an interest rate model that allows arbitrage, we can't possibly imagine using that model to price options. Because if you recall, the whole basis of option pricing is that we can price options because we can replicate them. And because we can replicate them, it must be the case that the price of the option is the same as the price of the replicating portfolio. Why is that? Because the market doesn't allow arbitrage. Namely, if the price of the replicating portfolio were different than the price of the option, the market could arbitrage that. So what drives option pricing are two things. One is that we can replicate options, and secondly, we're replicating those options in a market that does not allow arbitrage. And that's what ultimately provides us the unique price. So if we build a model which allows arbitrage in bond pricing, it couldn't possibly be useful to us in evaluating the price of options. We might develop replicating portfolios, but indeed we will be a dead end. We will not be able to say the price of our option must be the price of that replicating portfolio, because we know intrinsically the model already allows arbitrage, so how can we be assured that the market's not also equally arbitraging our option prices? So you see the dead end that is, and the reason that so much emphasis needs to be placed on this simple question: if you have an interest rate model or you have a model of bond prices, you need to verify that those models do not allow arbitrage amongst the implied prices. If they do, throw it away. It's not useful. And so that's the focus of our attention, is going to be on developing models that do not allow this arbitrage.